Hello everybody, welcome back to our discussion on quasi-geostrophic theory. Today we'll be doing our summary lecture looking at an idealized model of a baroclinic instability and drawing together all of the theory that we've discussed so far. So for a large-scale synoptic scale wave, we have the existence of a surface pressure low, which exists in the upswing of the wave, and a surface pressure high, which exists during the downswing. These are responsible for the generation of cyclonic and anticyclonic vorticity respectively, and hence lead to the development of this wave system. In the upper level, in order to support the geostrophic wind, we have 500 hectopascal pressures, which are high, low, and high, here existing at the crest, trough, and crest respectively. Note that the system then has a westward tilt associated with it, and this is responsible for driving the northward propagation of energy associated with the system. So the presence of cyclonic vorticity then leads to the development of a surface level wind field, which is then associated with cold and warm fronts. The cold air advection then exists in the trough region of the wave. This makes sense because in the trough region, geopotential heights are typically smaller than in the crest region, and so in the trough region this corresponds to thinner atmospheric layers and hence colder air temperatures. In the crest region we have larger values of geopotential and consequently thicker atmospheric layers associated with warmer temperatures. Typically the warm front and cold front at the surface exist in regions shown here with the red dashed line and the blue dashed line. The red dashed line here showing the warm front and the blue dashed line showing the cold front of the developing system. So as the wave continues to intensify, we're going to have the existence of absolute vorticity advection along the wave. This is going to be positive along the in the presence of the surface low and negative in the presence of the surface high for short waves. Looking at this in along a vertical cross section, recall the surface low is responsible for driving convergence of the ageostrophic wind at the surface and consequently drives a upward vertical velocity above the surface low. So convergence at the surface then leads to an upward velocity due to incompressibility. At the surface high, we instead have subsidence of air and consequently must have a downward velocity associated with air parcels above the surface high and consequently divergence of air at the surface. These are then also associated with convergence at the upper level above the surface high and divergence above the surface level low. So at the ridge we have relative vorticities which are negative. These are associated with anticyclonic rotation. At the trough we have relative vorticities which are positive, associated with cyclonic rotation. So then plotting this out in terms of red regions and blue regions, within the red region we have that the advection of relative vorticity by the thermal wind is positive, corresponding to a positive vertical velocity, whereas in the blue region we have that the advection of relative vorticity by the thermal wind is negative, hence corresponding to a negative vertical velocity. So this result then emerges from the quasi-geostrophic omega equation, which we use to relate the omega, or vertical pressure velocity, to the advection of relative vorticity by the thermal wind. Recall that the thermal wind here has a positive zonal component at all locations, corresponding to eastward motion within the wave itself. So if we look at the quasi-geostrophic geopotential tendency equation now, recall that there are two major terms driving the geopotential tendency. We have a propagation term, which is associated with the advection of absolute vorticity, and we have an intensification term, which is associated with differential temperature advection. So at the crest, we have positive differential temperature advection as warm air is being propagated northwards within this region, leading to a positive geopotential tendency and hence intensification of the ridge. So the differential temperature advection, that is the warm front passing through this location, has a tendency to intensify the geopotential and intensify the wave at this location. Cold air advection at the trough also intensifies the wave by driving the geopotential contours lower within this region, hence leading to a negative geopotential tendency. Propagation of the wave leads to geopotential tendencies which are negative and positive at the surface level low and surface level high, respectively. That is, the negative geopotential tendency at the surface level low is associated with the fact that the wave is going to be propagating to the east. Again, we're assuming a short wave in this case. So the trough then has a tendency to propagate into the red region in order to support advection of absolute vorticity. Analogously, in the blue region, we have a positive geopotential tendency, and hence the ridge will be advected eastwards in order to compensate for the fact that geopotential tendency is increasing within this region, and so the maximum will be moving into the blue region. So for short waves, we then have that the advection of relative vorticity is larger. So advection of relative vorticity is the dominant term in absolute vorticity advection, and hence is responsible for eastward propagation of the wave. If the wave were very long, like a synoptic scale planetary wave of large scale, generally at least 10,000 kilometers, this is then associated with westward propagation due to dominance of advection of planetary vorticity.